This is section 8.12, part D, and we're going to continue our discussion of sequences here. I did have a little bit of a problem with this video and I'm remaking it, so unfortunately my notes are already filled out, but I'll try to make sure I pace myself well enough that you'll be able to take notes as you watch. In this section, we're going to be looking at something called growth rates of functions. In the last couple of examples, it kind of raises an interesting question about how fast functions grow relative to one another. Knowing something about these growth rates can actually be sort of a shortcut that will help us more easily predict whether a sequence is going to converge or diverge. So here's a definition for us. We say that f of n has a faster growth rate than g if the limit as n goes to infinity of f over g is infinity, or equivalently, the limit as n goes to infinity of g over f is 0. So in other words, if the function with the faster growth rate is on top, the limit is infinity. If the function with the faster growth rate is on the bottom, the limit is 0. This is just a little bit of notation. We can write that if f has a faster growth rate than g, we use this double greater than. It doesn't just mean that the values of f are bigger than the values of g. It means that f is growing at a faster rate than g, or equivalently, g is growing at a slower rate than f. All right, so we're going to evaluate some limits of different types of functions and see if we can make some general conclusions. And these are going to be key. If the limit is infinity, we'll know that the faster growth rate is on top. If the limit is 0, we'll know that the faster growth rate is on the bottom. The first types of functions that I'd like to compare are logarithmic growth as compared to polynomial growth. So, we're going to take a look here and we're going to try and take the limit as x goes to infinity of a logarithmic function, and I'm choosing ln x, as compared to a polynomial function. Generically, I'm just going to call it x to some power, x to the n power. And notice that right now, as x goes to infinity, both the top and the bottom would go to infinity, meaning we have the infinity over infinity indeterminate form. That means that we can use L'Hopital's rule. So what I've got here is the limit as x goes to infinity. The derivative of the top would be the 1 over x. And the derivative of the bottom, we just use our power rule here. Bring the n down in front and reduce the power. So I have x to the n minus 1. Do a little algebra here. I'm going to take that 1 over x and just put that x down in the denominator. Right? So this x here just became this x to the first down there. And now I've got 1 over n and I can multiply those together. Adding the exponents, 1 plus n minus 1 just gives me x to the n. As x goes to infinity now, I have 1 over something getting infinitely large, and of course a finite number over infinity goes to 0. So, with a limit of 0, the faster growth rate was on the bottom. The polynomial had a faster growth rate than the log function. Right? That's a general conclusion, not for just those two, but for any polynomial and log functions. We can make that conclusion. Next, let's compare exponential growth to polynomial growth. An exponential function, I'm going to use the e to the x as my example of an exponential, compared to the polynomial, again, x to the n power, and we'll take the limit as x goes to infinity. Once again, right now, those both go to infinity. So I've got that indeterminate form that allows me to use L'Hopital's rule. Here's L'Hopital's rule. Derivative of the top is still e to the x. Derivative of the bottom, n times x to the n minus 1. Continues to be infinity over infinity. So I'm going to take L'Hopital's rule again. Derivative on the top, still e to the x. Derivative on the bottom, here's that n. This n minus 1, bring that down in front, decrease the power by 1. As x goes to infinity, still goes to infinity on the top, and that x still goes to infinity on the bottom. You're probably getting the picture, but here's one more iteration of L'Hopital's rule. Derivative of the top, still e to the x. Derivative of the bottom, I've got the n times n minus 1. And here's that power rule. Bring the n minus 1 down, decrease the power to n minus 3. We would continue to use L'Hopital's rule over and over and over. And the derivative on the top will never change, right? It'll always be e to the x. Eventually, with any polynomial, we finally get down to the point where the derivative is a constant. And you can see what's happening here. We're just multiplying by all the numbers, starting with n on down, which is the definition of n factorial. Finally, we'll get down to x to the 0 with the n factorial. The denominator becomes a constant. And so I have something going to infinity over something that's just a finite number, a constant. And so my limit is infinity. With the infinity limit, the larger growth rate was on top. So the exponential has a larger growth rate than the polynomial. All right, we've got a couple more to look at. The next one, I'd like to compare the growth rate of an exponential function to the growth rate of a factorial function. So here it is. My exponential goes on top, e to the x. Comparing it to the factorial, I put on the bottom, x factorial. As x goes to infinity, the top goes to infinity and so does the bottom. Back to that indeterminate form, not surprised. For the first time though, L'Hopital's rule is not going to help me. How come? We don't have a way of taking the derivative of x factorial, right? We've never talked about the derivative of that. So what I'm going to do instead is I'm going to use an algebra approach. On the top, e to the x literally means e times e times e times e over and over and over again, a total of x factors. In the denominator, x factorial means x times x minus 1 times x minus 2, etc., 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 down to 3 times 2 times 1. And notice there would also be x factors down there. So I'm going to break this fraction apart. And I'm going to say, let's just take the first factor from the top and the bottom, e over x, times the next ones, e over x minus 1, times e over x minus 2, and so on, all the way down to the last few, e over 3, e over 2, e over 1. A constant over x, which is going to infinity, constant over infinity goes to 0, right? Here and here and here. And by the time you get down to the last ones, e over 3, e over 2, e over 1, it really doesn't matter because 0 times all of this is still going to give us a limit of 0. So with a limit of 0, the faster growth rate was on the bottom. The factorial function has a faster growth rate than the exponential function. All right, one more. The super exponential, which I don't know if you've heard of that one before, but it's where both the base and the exponent have an x in them, right? Exponential functions have the variable in the exponent. Polynomial functions have the variable in the base. Super exponentials have the variable in both. I'd like to compare the super exponential growth rate to the factorial growth rate. So here we go. I'm taking the limit, super exponential on top, factorial on the bottom. Definitely infinity over infinity. And once again, L'Hopital's rule is no help because I can't take the derivative of x factorial. So I'm going to use an approach very much like last time. I'm going to say x to the x power means to multiply x by itself, x times x times x times x, etc., a total of x times. Denominator x factorial, x, x minus 1, x minus 2, etc., down to 3 times 2 times 1. Once again, let's break this up just like we did before. I can go ahead and cancel those first x's, just get rid of them. And then my next fraction would be x over x minus 1. And that would be multiplied by x over x minus 2, etc. The last few, x over 3, x over 2, x over 1. Okay. All right, these first couple, I actually can now use L'Hopital's rule, right? Infinity over infinity, derivative of the top is 1, derivative of the bottom is 1. Same thing here. Derivative of the top and the bottom, both 1s. By the time I get down to these last ones, however, as x goes to infinity, now I have infinity over 3 times infinity over 2 times infinity over 1. So multiplying stuff by infinity, definitely going to give me an infinite answer. Infinite limit means the larger growth rate is on top. The super exponential has a faster growth rate than the factorial. So, in order to use this in a useful way, let's consider one question, and then we're going to make a total list of all of our growth rates from smallest to largest. The quick question, would any of these limits have been changed if one or both functions included a constant multiplier? The answer is no. Remember that constant multipliers can always just get pulled out in front of limits. So that wouldn't affect the results, going to either 0 or infinity. 0 times any constant is still 0. Infinity times any constant is still infinity. So constant multipliers will not affect these results. Therefore, I can now be confident in saying, listing all of my growth rates from smallest to largest. Okay. Our first one, the log grew slower than the polynomial. Our next one, the polynomial grew slower than the exponential. I won't keep moving the camera, but the top of this page, we had the exponential growing slower than the factorial. And then our very last example, the factorial growing slower than the super exponential. So, this means, knowing these in order, if I'm looking at a limit and I can identify the numerator and denominator as any of these types of functions, I may be able to tell whether a sequence converges or diverges just by comparing the growth rates. If I have a function with a larger growth rate on top, my limit's going to be infinity, and my sequence is going to diverge. If I have a fraction with a larger growth rate on the bottom, the limit will be 0, and my sequence is going to converge. So this one's going to give me the divergent case. This one's going to give me the convergent case. So keep that list handy, and we're going to take a look at a few examples that make use of it. All right, in our examples, part A. As I look at this, I definitely have a polynomial, n to a power on top. The bottom is a log. The polynomial, remember, has the larger growth rate compared to the log. Larger growth rate on the top means the limit is infinity, and my sequence is going to diverge. Next one. Top is a polynomial. The bottom actually has both a polynomial and an exponential, and when that happens, always focus on the one with the larger growth rate. Between the polynomial and the exponential has the faster growth rate. So I'm going to call that exponential. And again, the exponential has the faster growth rate compared to the polynomial. Larger growth rate on the bottom converges to 0. C. This time, the original problem gave us just a list of numbers. It didn't give it to us in the formula form. So we're going to have to figure that out. And I'm going to notice that the numerators are all powers of 3, right? 3 to the first, 3 to the second, 3 to the third, and so on. So 3 to the n power on top. Denominators are that now familiar list of factorials. So n factorial on the bottom. Exponential on the top, factorial on the bottom. Growth rate for the exponential is smaller than the factorial. So smaller over larger, larger growth rate on the bottom converges to 0. Couple more. Again with D, we were given just a list of numbers. Here I'm looking at this numerator and seeing factorials. So n factorial on the top. On the bottom, these are all fourth powers. 1 to the fourth, 2 to the fourth, 3 to the fourth, etc. So n to the fourth power on the bottom. Numerator is a factorial. Denominator is a polynomial. Definitely have the larger growth rate on the top this time, meaning this one's going to diverge. The limit's going to be infinite. All right, and one more. Again, interpreting this, getting a formula for it. This is the one you haven't seen a lot of. This is the super exponential. 1 to the first, 4 is 2 to the second, 27 is 3 to the third, 256 is 4 to the fourth, and 5 to the fifth. So that was supposed to be an n. N to the n power, the super exponential on top. The bottom, these are all powers of 10. 10 to the first, 10 to the second, 10 to the third, so 10 to the n power. Super exponential actually has the largest growth rate of all of our functions, so definitely the larger growth rate on top. smaller on the bottom, meaning the limit is infinity, and that sequence diverges. All right, that brings us to the end of the sections 8.1 and 2 on sequences. We'll begin our study of series in the next video.